Okay, the first few pages of chapter 9b, I will just run through it very quickly because it's just a repetition of the knowledge in chapter 9a. Before we start, the yellow box on the top right corner, that should have caught your attention. This very thick black border of the box. Okay. Starting from 2020, the subtopics related to equation of plane have been removed from the P3 vector syllabus. Yeah, don't be too happy to see the word remove because you are a further math student. You will still need to learn it in the further math syllabus. So it doesn't really affect you. But if you are not taking further maths, then this will be a good news for you. Yeah. The reason why I put this remark here in the yellow box is that when you look at the old P3, when you look at the old P3 past years, if you see equations of planes, don't be surprised, because in the old syllabus, in the old P3 syllabus, the vectors chapter have equation of plane. And now CIE has removed equation of plane from P3 and they put it only in FP1. So in terms of the contents to learn, it doesn't affect you because you will still have to learn equation of planes eventually in about 1 or 2 weeks from now. Okay. Just for you to be aware that planes were actually in the old P3 syllabus. So when you see equation of planes in the old past years of P3, don't be surprised. Okay. Right. First page is nothing new. The two different ways of writing vectors, either in bracket form or either in terms of IJK. Scalar multiplication, you have seen this before. Scalar multiplication of a vector, it either lengthens it or shorten it or possibly reverse the direction. The length or magnitude formula is just the square root of each of the three components squared individually and you add them up. Okay. Parallel vectors, if two vectors are parallel, then you can write A equal to KB for some scalar K. Be aware that parallel vectors doesn't guarantee same direction. There are two possibilities. Parallel vectors can be having the same direction or opposite direction. Move to page 2. Okay. Collinear points, we have learned it before. If 3 points are collinear and you form any two vectors involving the 3 points, the two vectors that you form is guaranteed to be parallel to one another. Okay. Unit vector is a vector divided by its own length, and by the word unit, it means the length is exactly 1 unit. Okay. Next, on position vector. Position vector by default is the vector directed from origin O to that point. It's a position vector of a point P. I think I should mention the word P here. The position vector of a point P. Please add in the P here. I think the P is missing. With respect to a fixed point O is a vector OP. O directed to P is known as position vector of P. And similarly, position vector of Q, it will be OQ. Okay. Right. Then this box here is just the subtraction formula. PQ can be written as O to the end point minus O to the starting point. We have used this multiple times in chapter 9a. Then move on to ratio theorem. Ratio theorem is a little bit new, so I will be a little bit slower for ratio theorem. Okay. But in the previous chapter, we have covered the midpoint formula for vectors. Okay. Ratio theorem is just a more general formula, and the midpoint formula will be a special case of the ratio theorem here. Okay. If you can recall in the chapter of coordinate geometry, we also learned something similar where you want to break a line segment into two parts. Let's call the points A and B. You want to break the line segment into two parts, but C is not the midpoint. And let's say you want to break it into parts with ratio 5 and 2, where AC ratio CB is equals 5 to 2. Okay. So if you can recall in coordinate geometry, if this coordinate is x1, y1, this coordinate is x2, y2, and then you would associate this 5 with the further point. You will associate this 2 with the further point. And then to obtain coordinates of C, it's just two fractions. The denominator is always 5 plus 2. And then at the numerator, you will take 5 multiplied with x coordinate of B. So you have 5x2, then plus with 2x1. And then do the same for the y coordinate. You have 5y2 and plus with 2y1. So this gives you the formula to get the coordinates of C. Okay. So if you can remember the formula for coordinate geometry, then vector is just a formula of a similar form. And the idea is exactly the same, just that now we write everything in vectors rather than coordinate. Okay. So this will be also applicable to 3D, and not only 2D. This idea is also applicable to 3D. So for the case of vector, okay, so let's make a comparison. Okay, I mentioned midpoint first. I scroll further down. I mentioned midpoint first. Okay, so if M is a midpoint of A and B, if M is a midpoint of A and B, to get the coordinates of M, you have x1 plus x2 over 2, y1 plus y2 over 2. A is x1, y1, B is x2, y2. Okay, for the case of vectors, what you have is you have OM is equal to OA plus OB divided by 2. So if you compare the formula for vector with the formula for coordinate, x1 will correspond with the position vector of point A, while x2 corresponds with position vector of point B, and you refer back to the diagram. And so it's of a similar form. It's still A plus B over 2. A plus B over 2. And the difference is that for coordinates, you use a coordinate, and for vector, you use position vector. It's the same format. It's still A plus B over 2. Okay. So now go back to the ratio theorem. Okay. So according to the ratio theorem, right, if I want to convert this into a formula for vector OC, okay, so your intuition will tell you that this will be 5 plus 2 at the bottom, right? Then x2 will be replaced by OB. x1 will be replaced by OA. Then done. This will be the formula for ratio theorem. It has a similar form. x2 corresponds with point B. x1 corresponds with point A. This is actually a correct formula. Alright, so if you can remember the formula for coordinate geometry, here it just comes to you naturally. You don't have to memorize separately. It's the same thing. In fact, the formula for vector is neater. It's neater or shorter because the position vector already takes care of x, y, z coordinates in one go. Right? So you don't have to deal with x, y, z coordinates separately because the position vector already carries information on x, y, z coordinate. Yeah. Okay, so that's what the formula in the box is trying to tell you. So if you refer to the diagram, C divides the line segment AB in the ratio lambda to mu. Okay, so you would have your lambda associated with the further point B. You would have mu associated with the further point A. And you have lambda times OB. Okay, maybe I should color this in green. Lambda times OB and plus with mu times OA. And then the bottom is just the sum of the two numbers, lambda and mu. Okay, that's it. Okay. Now, special case of ratio theorem. If lambda and mu are both equals to 1, that means C becomes a midpoint. Right? If AC dot CB, AC ratio CB, the ratio is 1 to 1, that means C is exactly the midpoint. C will become the midpoint of A and B. C becomes the midpoint. Yeah, so fill in the word midpoint at the space here. So when C is the midpoint of A and B, then you can just sub in lambda and mu both equals to 1 in the formula above. Then you will have the formula OB plus OA, 1 OB plus 1 OA divided by 1 plus 1, that will be 2. And this will be consistent with the midpoint formula that we learned in chapter 9A. Right, so it's basically nothing new here. Okay, so the purpose of me stating this special case is I want you to be aware that midpoint is just a special case of ratio theorem. Ratio theorem is a more general formula, while midpoint is just one specific case of ratio theorem, when the ratio is 1 to 1. Right, and that's it for this part. And exercise 1 is rather simple, so I will just skip exercise 1. This is rather simple, just for your own practice. I will just skip exercise 1 and I will move to scalar product. Okay. Scalar product, the first 5 points are also a repetition. The first 5 points on page 3 is exactly a repetition of what you saw in chapter 9A notes. So I will just skip through all this, and you can just read on your own. Now, application of scalar product. This formula for cos theta, you have seen it before in chapter 9A. Again, a repetition. The only thing new here is this yellow box on the right. Okay, so let's have a bit of discussion about this yellow box here. Okay, what can we say about the size of the angle theta? So it's actually referring to the cos theta formula. It's referring to the cos theta formula of A dot B divided by length of A, length of B. And this is in the process of finding angle between two diverging vectors A and B. Okay, now, what can you say about the size of the angle theta when A dot B is positive, negative, and 0? Okay, so when A dot B is positive, okay, so if you look at the right-hand side, of this equation, okay, the bottom is guaranteed to be positive. And this is 100% positive. Because A and B are both lengths. Lengths are guaranteed to be positive. So if A dot B is positive, the top is positive, the bottom is positive, that means the entire thing becomes positive. Yeah, so Daniel has responded in chat, acute, obtuse, and right angle. Yep, correct. Yep. Yeah, so that is the correct answer. Yeah, so you notice that so let's talk about situation A first. If A dot B is positive, then the entire fraction becomes positive. So you have then cos theta is positive. Right, so when cos theta is positive, and by the word positive I mean strictly more than 0, then cos theta is strictly more than 0. If you refer to the cos function, I only consider until 180 degrees. This is a cos function from 1 to 0 to minus 1. This is 180 degrees. Okay. So if cos theta is positive, that means you consider this section of the graph. Right? Then the angles that you will get will be from 0 to 90, including 0, not including 90. Therefore, theta must be between 0 to 90, possibly 0, but it can't be 90, because I have strictly more than 0. Yeah, so here you can say theta is either acute or possibly 0. And because acute angle doesn't really include 0, so yeah, so it's possibly acute or 0. Okay, then if A dot B is negative, negative means strictly less than 0, then cos of theta will become negative. Because you have a negative numerator divided by a positive denominator, negative number divided by positive number, the whole fraction will become negative. So cos theta will become negative. Okay, so when cos theta is negative, looking at your cos graph, if we are only looking at quadrant 1 and quadrant 2 angles, because angle between two vectors is always between 0 to 180, you can't have any larger, right? So you only look at the first two quadrants. So if your cos theta is negative, the black color diagram is actually y equals cos theta. So you will look at this pink color section of the graph. Okay, so your angles that you will get is possibly theta is between 90 to 180, possibly equals to 180, but not including 90, and because our cos theta is strictly negative, it doesn't include 0 itself. So here we can say theta is obtuse, or 180 degrees. Obtuse doesn't really include 180. So it's either obtuse or 180. Okay. But when A dot B is 0, yeah, this one we know lah. Theta is a right angle. Okay. Okay, so that's it. Okay, so this box here is just for you to be aware. Just by looking at the sign, as in the plus or minus sign, just by looking at the plus or minus sign of the numerical value of A dot B, you can tell whether you expect an acute angle, an obtuse angle, or a 90 degrees. Right. Next, perpendicular vector, nothing new. Projection. Okay. Projection is something new for you. It will not be asked. I mean, it will not be really needed in chapter 9B past year questions. But projection will be required for your understanding of FP1 vectors. Right, so it's important to understand the idea of projection here. So first of all, what does projection means? Okay. So let's read through the sentence first. The projection vector of A onto the direction B. Usually, when the question mentions a phrase like this, they might omit the word the direction. And so even if they say the projection of vector A onto vector B, it means project A onto the direction of B. And so this phrase in green, even if they omit, you can insert this phrase on your own. Okay, so it's the vector C. So you can imagine like C is the so-called shadow. A shadow is a very informal word, but it's very useful for understanding. And so the layman way of understanding projection is shadow. C is the so-called shadow of A. the shadow of A in the direction of B. And so to obtain this shadow accurately, you need a 90 degrees. And so you can imagine something like this. Um, if you want to project A onto B, you would imagine that light comes from a direction that is perpendicular to B. Light comes from a direction that is perpendicular to B. And when you shine the light on the vector A, the arrow C will be the shadow of the vector A. It will be the shadow of the vector A. And this C here, the length will be exactly from the starting point of A up until this point, which is 90 degrees coming down from the tip of A. And this point we have a name here, which we'll introduce later. This is actually the foot of perpendicular. So if I name this point as A, if I name this point as P, and if I name the dotted line as L, then this point here is the foot of perpendicular. If I call it F, F is the foot of perpendicular from P to L. Rongjie says CGI. What is CGI? I don't understand CGI. Okay. Oh, I know nothing about computer graphics. Yeah, so I can't answer you. Okay. Right. Okay. So yeah, this is a shadow idea. So can everyone understand the shadow idea? Do you want me to explain again what I mean by shadow? So make sure you understand what I mean by shadow here. When we say projection, the layman way of understanding it is shadow. Yeah, in SPM Max, you have something similar. In SPM Max, you call it orthogonal projection. Yeah, it's a similar idea here. Yeah. And so you imagine that the light comes from a direction perpendicular to B, and then when the light shines from above, in the shadow, you call it a projection. Okay. Yeah. The proper term to use is projection. In the exam, you don't use the word shadow. The shadow is just my way of telling you the idea. And the proper word to use is projection. Okay. Amanda asked in chat, is it something like resolving a vector except we only draw out the horizontal component? Yeah, you can imagine it this way. Yeah, you can interpret it this way. Actually, if you take your B as the horizontal direction, then the vector C will be the horizontal component of A. Yeah, you can interpret it this way. That is under the assumption that your B is regarded as your horizontal direction. Then you can interpret it this way. Okay. Right. Okay, so if everyone can accept this idea of shadow, I will then proceed to the formula. Okay. Okay. There's a story behind this formula, but because we are rushing to finish the syllabus, I will skip through the story. And so unfortunately, I have to skip through the story because we don't have time to go through the story. And so you just accept that the formula is like this. Or maybe a shortened version of the story, just for your better understanding. I will not tell you the full story, but I will tell you the shortened version. Okay. The story is this. Um, okay. Here in the printed diagram, uh, theta is printed to be an acute angle. But this formula also works when theta is obtuse. Right, this formula also works. So I'm talking about this box here. The formula in the box for length of projection, it also works when theta is obtuse. And so I will draw another similar diagram where B is the direction of L. Vector B is parallel to line L. I still have my vector, so my vector A is still a slanted line starting from point A on line L, but let's say it slants in a different direction. Let's say it slants this way. Let's call this my vector small a. Okay. Now, what is the angle between vectors A and B then? Okay. This theta here is defined to be angle between vectors A and B. A and B are diverging. As you can see, you can always move your vector B such that it starts from point capital A. A and B are diverging. And so theta is actually angle between A and B. So if I apply the same definition for theta, so my theta will become this position. And my projection vector, if I shine the light from above, my projection vector will be then like this. And my foot is here. This is my length of projection. The red color length is the length of the AF. AF will become the length of projection. Okay. Now, because I don't have time to tell you the full story, I will only focus on the case where theta is acute. But just be aware that the same formula also works when theta is obtuse. Right? Okay. So looking at this diagram when theta is acute, okay. Looking at the right angle triangle PAF, we are interested to get the length AF. Our aim, get the length AF. Let's be clear with the aim. Aim is to get the length AF. You have this name as vector A, this name as vector C. Here is theta. Okay. Now, making use of the right angle triangle, by basic trigo, you know, cos of theta is AF adjacent divided by hypotenuse, which is AP. Okay. Now, what is AP and what is AF in terms of the vector? AF is the length of vector C, modulus C, right? What is AP? AP is length of vector A, according to my diagram. Okay. Then, if I make length of C my subject, because my aim is to get length of AF, which is also the length of vector C. Okay. Now, if I make length of vector C to be my subject, I get C equals length of A times cos theta. Right. Now, recall the alternative formula for dot product. What is A dot B? We have defined theta to be the angle between A and B, so we can safely use this as length of A times length of B times cos theta, where theta is the angle between vectors A and B. Okay. Now, if I make cos theta my subject, that will be A dot B divided by length of A, length of B. Okay. Now, it's time to do substitution. Sub this thing to replace cos theta. And then what we get is length of C is length of A times A dot B divided by length of A, length of B. Length of A, length of A, these are just some positive numbers which are equal, so you can cancel. you end up getting A dot B divided by length of B. Okay, so this will be the formula for length of projection for the case when theta is acute. Hey, when theta is acute, your A dot B is guaranteed to be positive, right? So it doesn't matter even if you don't put modulus over here, you still get a positive answer, which makes sense. And because this is a length, length must be positive. And so whatever answer that you get at the end, it must be positive, must be positive. Right? However, just now I say we want the same formula to be applicable even for the case when theta is obtuse. But the problem about theta being obtuse is that when theta is obtuse, the dot product becomes negative. And when theta is obtuse, A dot B becomes negative. There's a long story behind how you can obtain a similar formula when theta is obtuse. I'm not going to tell you the story, but just accept that for the formula to be applicable, even for the case when theta is obtuse, the way to fix it is you just introduce modulus above. And then the formula will be applicable for both the case when theta is obtuse and also for theta is acute. Okay. So regardless of whether theta is acute or obtuse, it's length of projection. This is length of projection. Will be A dot B divided by length of B, and to deal with the possibility of A dot B being negative, you just use modulus to fix it. Then you are guaranteed to get a positive length for projection. And so this will be the formula that is applicable regardless of the size of theta. So just remember this formula is A dot B over B. If you're interested to know the full story, yeah, unfortunately, we don't have time to go through the full story. You can try to search online, or you can even try to figure out the story yourself. Yeah, it's not too hard to figure out the story yourself. Or you can try to search online. Unfortunately, I can't cover the story for you. What's important in the exam is that you know how to apply this formula. Exam won't ask you to tell story, so don't worry for exam purpose. Okay, now, while this formula is quite easy to memorize, it's A dot B over B with modulus for everything. You should remember what are the positions of vectors A and vector B. Okay, so when you apply the formula, and so later in when we solve questions in a later part of the chapter or in the next chapter, the points or the vectors, it will be named differently. They will not be so kind to name the appropriate vectors as A and B. So you will need to know what your A and B actually represents. Okay. So what is the vector A then? Okay. Vector A is the slanted vector from a point on line L to the external point. Vector A is a slanted vector from a point on L to the external point. I call external point, I use this term to refer to the point P, the point that doesn't lie on L. Okay. Then what is vector B then? Vector B is a vector parallel to L. And so when you visualize the diagram, you will have your dotted line L. B is just any vector parallel to L. Whether B points to the right or to the left is not important. The same formula will still work. Okay. And even if you take the lengthened version of B, it will still work. B is just any vector parallel to L. Okay. Then it is the vector A. Okay. So what is C then? Okay. C is the projection of vector A onto the direction of B. And so A is the vector whose shadow you want to find. A is the vector whose shadow you want to find. So you have your vector A like this. And this formula will lead you to the green color length. This will be length of projection. So the formula will give you the green colored length. Okay. Okay. So length of projection is very important. Make sure you know how to apply the formula. Okay. Then I move on to the next one. Okay. Projection vector itself is not so important. Okay. But since you can find the length of C, it's also possible to get the vector C itself. But getting the vector C itself is not so important in our syllabus. Most of the time, we are only interested in the length of the projection, not so much about the vector of projection itself. Okay, so part B, I would say, is less important. To find the projection vector C, you use the formula vector C equals to A dot B hat times B hat. So what is this thing? So first of all, in the length of projection formula, notice that there is an alternative formula given at the back. It can be written as A dot B hat. This is just a simple algebraic manipulation. So I hope some of you are already aware how to obtain the alternative formula from the first version of formula. It's actually very easy. First of all, I think I need to clarify that the modulus at the right-hand side of the formula, they mean different thing. The pair of modulus on top is the usual modulus that would make a number positive. This is the usual modulus. Because A dot B is a number. If A dot B happens to be the negative, that modulus removes the negative. But the pair of modulus at the bottom is a notation for length. At the bottom, we are finding length of vector B, so don't get confused. The modulus have different meaning. Okay. Now, I can always rewrite this thing as 1 divided by B, where modulus B is just some positive number, right? 1 over modulus B, modulus B is just a positive number. So I can always rewrite this as 1 over B times with modulus of A dot B. Okay. Now to make sure everyone can see, let me just introduce lambda. Okay. I let lambda equals 1 over B. Okay. But then what is lambda? It's just a positive scalar. Okay. Then lambda is just a positive scalar. Because it's just 1 divided by a positive number. Okay, so let's rename 1 over modulus B as lambda so that everyone can see easily. Lambda A dot B. Okay. Now, because lambda is a positive number, it remains the same even if I put modulus to it. Right? Modulus of lambda is the same as lambda. Okay. Now, so recall properties of modulus. The red color modulus is a usual modulus. The blue color modulus is also a usual modulus because A dot B is a number, lambda is a number. So recall for any x, y in R, modulus of x times modulus of y is equal to modulus of xy. That allows us to combine the two modulus. So I have lambda times A dot B. Now, at the underline section, recall the properties of dot product. We are allowed to stick the lambda to A or stick the lambda to B as we wish. Right? This time I stick my lambda to B. So it becomes modulus of A dot with lambda B. Okay. But then what is lambda B? What is lambda B? Okay. Right. At my side working, let's see. What is lambda B? Lambda is what? 1 over modulus B times B, which is equivalent to B divided by its own length. And what is this? It's B hat. Okay. So we end up getting A dot B hat. Yeah, so that's how we got the alternative formula. It's just a simple algebraic manipulation. Okay, so I will suggest you to memorize the first version of the formula. No need to memorize the second one because the second one is not useful for computation. B hat is usually quite messy numerically. When you have numerical values, B hat is actually quite messy. So I would prefer you to use A dot B over B. The computation is less messy if you use A dot B over B. Okay. So I will suggest you to memorize the formula that I color in light blue there. The one in yellow, you don't really have to memorize. Okay. Yeah. Okay, then coming to point B, to find the projection vector C itself, it says you can use this formula. Okay, so here in bracket, I tell you the idea of this formula. It's actually the length of vector C multiplied by the unit vector in the direction of B. Okay. Refer to my diagram above, to my printed diagram above. Maybe I just redraw it here. My vector B is parallel to line L. And I know my vector C is something like this, which could be longer or shorter than B. Okay. Now, it says that it's just the length of vector C multiplied by the unit vector in the direction of B. So if I want to get a formula for the vector C, what I need is I just need to shrink the length of B to become unit vector. I just need to find B hat with length 1 unit. Then to get the vector C, I just need to lengthen it, lengthen B hat by a factor that is equal to the length of C. Okay, so if I give you some numbers, if I say length of C is equal to, then vector C is just 4B hat. Right, because B hat has length 1 unit. Right, so it's the same idea here. Okay. So what is A dot B hat? If we refer to the projection formula, I mean length of projection formula up there, it's actually the length of projection. Right, so this number here is actually length of projection. And then multiplied by B hat. Yeah. So it's the same with my numerical example here. What is a 4? 4 is length of projection. Okay, and multiplied by B hat. Okay. Now there is a question that maybe some of you may wonder. Okay, length of projection, the formula is what? The formula is actually A dot B over B with modulus to everything. And after some algebraic manipulation, it is modulus of A dot B hat. Okay. Now the question is, why in the projection vector C, we are not putting modulus here? Why do we use bracket A dot B hat but not modulus A dot B hat? Why are we removing the modulus here? Well, again, there's a long story. I'm not going through the long story here. It's actually to take care of the possibility of theta being obtuse. It's to take care of the possibility of theta being obtuse. Okay. So here they say, if the scalar product A dot B has a negative value, then you would get a projection vector in the opposite direction of B. Okay. So they say if this value that I circle, if it is a negative value, then let's say C is equal to minus 4B hat. Then diagrammatically you will get B hat pointed this way, but your C will point the other way. Okay. Under what situation will we have C pointing the other way? It is when the angle between vectors A and B is obtuse. Right? Because when your A points to the other way, the shadow of A will point in the opposite direction of B. Right? So if you want to find the projection vector C, right, you just use the formula. Okay, so to get the projection vector C, you just use the idea of using the length. Okay, yeah, the idea is length of projection, right, multiplied by unit vector in the direction of B. Right, but one thing to take note of is the length of projection, you're going to remove modulus. You're going to remove modulus to take care of the possibility of theta being obtuse. Okay. So what is the formula for length of projection? It's A dot B over B. Right, the usual formula is modulus to everything, right? You would remove your modulus from the numerator. Okay. This is not a usual modulus. The bottom pair of modulus is length, right? So you do not remove it. Okay. Then what is unit vector in the direction of B? It will be B divided by B hat. B divided by length of B. Yeah. So you just need to multiply these two. Multiply these two. Okay, and you will get the projection vector. Right, for exam purpose, projection vector, I would say 99% you will not be asked to find projection vector. What's more important is you know how to find the length of projection. I know projection vector is a bit hard to understand. The idea is you take the length multiplied by the unit vector in the direction of B. It's just like that. Right? Because if you look at the simple diagram, when theta is acute, this is B, this is C. Right? So you just need to shrink the vector B so that the length is 1 unit and then magnify it by the length of C. Right? So it's the same idea. If you still find this part difficult to digest, I suggest you to watch the recording later for our lesson today when you are free. If you still find it hard to digest, just watch the recording. Okay. For exam purpose, no need to worry about projection vector. Most of the time, it's only the length of projection that you need to care about. Okay. Okay. Right. Exercise 2, finding scalar product or dot product. This is just simple computation. I leave it for you. Angle between two vectors, you also know already. Perpendicular vectors means the dot product is 0. You also know already. Then parallel means one vector is a scalar multiple of the other. You also know already. So I leave all of this for your own practice. We don't have time for this. I have to move on to the new subtopic here. We still have 10 minutes, so I will start with a very brief introduction. Lines in 3D. Diraj say, it's not projectile, it's projection. We don't call it projectile. Yeah. Projection vector is the length of projection times the unit vector B. Yep, correct. It is a length of projection times the unit vector of B. But remember, you have to remove modulus. You have to remove modulus from the formula of the length of projection. In the original formula, there was a modulus at the top, but now you remove it. To allow vector C to point in the opposite direction if theta happen to be obtuse. Okay. Now let's move to section 9.3, lines in 3D. Okay. First of all, point number one, by the word line, we are referring to a straight line of infinite length. Especially in this chapter, when you see the word line, always assume that the line can be extended indefinitely. That means if you are given 2 points A and B, especially in this chapter, when they mention the word line AB, it means not only this short part here, but it's extended indefinitely. So this entire thing, extended indefinitely, will be the line AB. So it's not only the short section from A to B, it is AB extended indefinitely. Vector has a fixed length, line has infinite length. Notice the wording used. Okay, so if it is a vector AB has fixed length, okay, but line AB has infinite length. Yeah, and so be careful with the terms used here. Fixed length, Length, okay. Yeah. Right, so this is the first basic understanding. Line has infinite length, especially in the chapter of vectors. So point number two, since our exam questions are 99.9% three-dimensional, so we are of course talking about lines in 3D here. A line in 3 dimensions, it can be defined. So the phrase can be defined means that if you are told 2 points on a line, you can already get the line. You can already get the equation of the line. Or if you are given a point which lie on the line and the direction vector of the line, then you can also get the equation of the line. Okay. Direction vector is a new concept that many of you have never heard before. So to understand what the meaning of direction vector is, I will have to explain it using 2D first. And then the same idea is applicable to 3D. Let's consider a two-dimensional line first. Okay. Consider a 2D line with the usual equation, let's say y equals 2x plus 1, a simple one like this. In a 2D diagram, we can easily draw the graph. And now we are going to interpret this in a different way, right? But let's draw the graph first. Y-intercept at 1, and let's say I select a point here. I select a point when x equals to 1, I know y coordinate is 3. You can easily compute the y coordinate, right? So you have this point 1, 3 here. Let's call this point A. Let's call this point A 1, 3. Okay. Now let's take a different point. Let's say I take x equals 2. Okay. At point B, my coordinates is 2, 5. Okay. Now, let's find the vector AB. Let's find the vector AB. AB is OB minus OA. 2, 5 minus 1, 3. You get 1, 2. Okay. Okay, so AB is a vector 1, 2. Okay. And this is a vector AB. Okay. Now, let's consider a general point on the line. If I call this line L, okay, consider a general point. R with coordinates x, y on the line L. The meaning of general point means it can be anywhere along the line. That's why I'm not putting any numbers for the coordinates. I just call it x, y. R can be anywhere along the line. Okay. My R can be here. My R can be somewhere in between A and B. My R even can be at the bottom end, or maybe even further down. R can be anywhere. Now, the equation of line, so we know xy will satisfy this equation. For example, if my R happen to overlap with B, then it is always true that 5 is equal to 2 times 2 plus 1. And you can just sub in the xy coordinate. Right. So yeah, any general point, it will satisfy the equation of the line. This is our usual understanding. So now let's try to get a formula, get a vector equation. This equation is called the Cartesian equation. This is actually Cartesian equation of the line. A Cartesian equation means it's given in terms of x and y. Now let's try to get a vector equation. We introduce a notation. Let R be the position vector of the general point Rxy. Okay. Then R is actually the vector from O to R, right? Okay. Then next, okay, we have 3 more minutes. Okay, just tell you a very quick idea first. Okay. Now, my R can be anywhere along the line, right? My R can be very far up here, it can be somewhere in the middle of A and B, it can be very far down here. Okay, now, regardless of where my R is, I want to find a path that will lead me from O to R. So one path that I can take is I take the path from O to A first. Take the path from O to A, then depending on where my R lies, I will take a scalar multiple. I will take a scalar multiple of AB. And so the lambda AB that I draw here is a lengthened version of the red color vector, which means my lambda must be a positive number greater than 1. And so lambda can be possibly 2 or 3 if I want to reach a far away point. If my R is even further, then I just need to modify my value of lambda. So yeah, so I just need to take lambda AB for an appropriate lambda. For an appropriate lambda. Then what if my R is down there? If my R is down there, getting from A to this far point R here, I can also take a scalar multiple of AB, of course, for a different lambda. This time, of course, my lambda needs to be a negative value because I'm going in the direction opposite of the red color. So what we have here is, regardless of whether my R is somewhere far away at the top or somewhere at the bottom, it's always possible to reach it by taking the path OA followed by lambda AB. OA followed by lambda AB for an appropriate value of lambda. So we can write like this. OR can be written as OA plus lambda AB. And to cover all possibilities, to cover all possible positions of R along the entire line, then we should allow lambda to take all real values. At the time is now 3 o'clock, I will pause here. I will continue this story tomorrow morning. It's important for you to understand this story before we move to 3D vectors, the 3D lines. So I will continue this story tomorrow morning. Tomorrow is Friday, so as usual, we start at 7:30. Let's see you tomorrow morning at 7:30. Thank you, everyone. You may leave the video meeting.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Have a nice day.
Thank you, sir. Bye, sir.